let's now see if we can improve the situation. Up to now, we've seen that free fishing doesn't lead to a very optimal situation because since firms are free to enter the market and rent as many boats as they like, then they do until essentially there's no difference between renting a boat and doing the optional alternative situation activity. On the ecosystem side, it's not much better since it can lead to quite depressed fish stock, especially if the fishing technology improves a lot, like with trawling, for instance. So here I have reproduced the situation with free fishing. So this is, as a reminder, so on the x-axis, the number of boats, and on the y-axis, the profit per boat. If there is a single boat that fishes in the ocean, then it's a very good, very profitable activity because the stock is the whole ecosystem carrying capacity. So the catches are very good, and the profit per boat is the price multiplied by the catches for that boat, which is alpha k, and the cost per boat is just c. The problem is since anybody can enter, then slowly but surely other boats join the fray, and they do that until essentially the revenue per boat equals the cost per boat, at which time it's not profitable anymore to fish in the sea. So if imagine you're a small government and you have your small interns sea, and you would like to maybe improve the lot of the livelihood of your fishermen, and maybe have some extra taxing revenue from that industry. What could you do? Well, one reflex we would maybe have is to just say, oh, let's just nationalize the whole industry and have the government administer it. Okay, one alternative would be to say auction the right to fishing, and just say, oh, we're going to allow for a single firm to control the total number of boats in the sea, and then choose optimally the number of boats that would maximize its profit. And then since it's an auction, then that firm would essentially pay the government to have the right to exploit this resource. In both cases, we can see that it would lead to the same situation. So that would be the probably a better solution. So let's see what this would look like mathematically. So imagine that it's a central planner, or it can be just a monopolist, who chooses the number of boats to maximize the total profit in the fishing industry. So then what is the objective function? The objective function is to maximize the whole profit in the industry. So let's write this as capital Pi of, and then it's a function of obviously the number of boats in the industry. And now, of course, we only care about the steady state equilibrium. So what do we choose as our control variable? Well, a choice variable, we choose B star. And what is this total profit? Well, it's B star that multiplies the profit of one boat. Of course, all boats are the same. That's simpler. So it's pi multiplies B star. All right, and so I can just write what is pi. So it's B star that multiplies, so P alpha. And then let's just, for now, put the stock, so the whole stock of fish. That is a function, of course, of B star. And then the cost for a single fishing boat is just C. So what is the difference? Well, before we had that fishing boat entered as long as the profit was positive. So at the equilibrium, we had that this P alpha S star of B star minus C equal to 0. Now it's a bit different. Now what we want is to maximize this whole expression. And we see that there are actually two ways in which B star impacts the total profit. One is, of course, at first glance, if I have more boats that exploits the resource, then it's better to have better profits. But as we know, we have more boats, then it depresses the equilibrium stock of fishes. So here there's going to be this other aspect to take into account. How do I perform this maximization? Well, I just take the first order condition with respect to B star. So first order condition. So I derive profit with respect to B. So the profits of B star. And then let's already establish that now we're going to find some specific B star which is different from before. Before we had B star F for free fishing. So now let's write this as B star O for optimal B star. So I could also have written B star M for monopoly B star. So let's write B star O. DB star. So here I don't have to write O because it's just indicating that I'm deriving this thing with respect to B star, but then I'm going to express it at the value of B star O. So this is equal to, well, let's derive first with respect to the first B star here. So I get just this expression in the parenthesis, and then plus B star O. Yeah, let's not forget my O here. Plus B star O. That multiply the derivative of inside with respect to B star, which is simply going to be P alpha and then D S star of B star O. And then C is a constant, so D B star. And then since I'm maximizing, I'm setting this to 0. So we have found so that this is exactly what we had for the free fishing. So this was equal to 0 in the free fishing, and now there is this extra term. And just to see if you're following, so just think a bit. Is this extra term going to be positive or negative? Well, it's going to be negative because ds dB star is negative. The more boats in the ocean, the lower the equilibrium fish stock. So let's now compute what is going to be B star O. So I'm going to have that. So let's put all the revenues on one side and all the costs on the other. So the revenues is, first of all, this term here is a revenue, plus this term here is part of it's the marginal revenue. And this is going to be equal to, so I just add C on both sides. So I get C. So again, I'm going to add, so this is the marginal revenue from extra boat. And this is the marginal cost from an extra boat. All right. So before we found that the solution was that P alpha S star BO was equal to C. And now it's not exactly going to be this. And we can already guess that probably the optimal number of boats should be lower than before, because we established that the boats in the free fishing industry was the number of boats was quite high. So let's just go ahead and compute it numerically. So we have P alpha, and then we can substitute S star of P star O, which is, if we recall, k multiplied by 1 minus alpha, so B star O divided by R. So this, we found that using our the fishing dynamics equation. So we just have to go back and look at that. Plus B star O P alpha. And then this, so it's going to be the derivative of S with respect to B. So the derivative of this thing here, and we see that we have K, 1, I don't care, and minus alpha divided by R. So K minus alpha divided by R. And this has to be equal to C. And what just happened there? Well, so you see, if we look at what we have P alpha K that multiplies 1, and then P alpha K times alpha BO divided by R, which is the same as BO P alpha K alpha divided by R with a minus sign in front of it too. So we get P alpha K minus 2 yeah, let's write it this way. P alpha squared K divided by R multiplying B star equals C. So it looks pretty much like we had before, but now we have a 2 that just appeared here. And let's go ahead and find out what is the analytical solution for B star O. So B star O equals to, so let's multiply by minus 1, and let's have this on that side. So I get P alpha K minus C, but then let's multiply by R and divide by P alpha squared K, and there is a 1/2 here. And I can even simplify this and find that B star O equals to, so here I'm going to have, yeah, let's have 2 alpha here, and then here it's 1 minus C divided by P alpha K. All right. So here the B star O has a 2 in front of it, and this came from the addition of this extra term. So this may remind you that in the free fishing industry, the solution looked almost identical, but we didn't have a 1/2 here. And in fact, I can write what we had in the free fishing industry. It was exactly B star F that was equal to R over alpha times 1 minus C divided by P alpha K. So I could just write that B star O equals to 1/2 B star F. So the intuition that we had too many boats in the free fishing industry was right. So what would a monopolist do? Well, he would decide to put fewer boats in the sea, so that the costs per boat are, so we have fewer times to pay C because we have fewer boats, and then each boat is able to catch more fishes. Because the fish stock is going to be higher, as we are going to find out. And this looks exactly what a monopolist would do in any monopolist market. We would just decide to have a lower supply to make sure that the demanded price is higher. such as to maximize its profit. And we can actually look at what this looked like. So it looks like this. So we have that. This was we could say average revenue per boat, which was equal to average cost per boat in the free fishing industry. Now we have that the marginal revenue per boat is going to be equal to the marginal cost per boat. And this should remind you of your what you learn in terms of monopoly. So if we have a linear demand, then the marginal revenue was exactly 1/2 the value of the demand. So it's exactly what we find, and that this explains why B star O is exactly 1/2 of B star F. And in terms of profit, well, before our industry didn't have any profit because we were in that case, but now we see that there's a gap between markup, we could say, between the revenue per boat and cost per boat. And so the profit of the industry is the number of boats multiplied by the average revenue, so revenue minus cost, so a profit per boat. So this is this expression here. So now we have all we need to find out all the other variables to find what is the equilibrium in the socially efficient fishing situation.